So for the plane stress condition, because we are analyzing a plane stress, of course, we are trying to model a plane stress problem. We have to select the appropriate constitutive matrix or the D matrix. We already discussed that for plane stress and plane strain conditions, the D matrix, constitutive matrix, differs slightly. And for the plane stress condition, D can be written as, so now all the mechanical and the material properties get into the picture. Modulus of elasticity of the element related to Poisson's ratio, and one new, we have a neat equation which is related by different terms of the materials, or material related by different material properties, or which includes material properties. Since we are given the material properties, where nu should be taken as 0.3, the Poisson's ratio, the modulus of elasticity, 30 times 10 to the power 6 pounds per square inch. D can be written as 30 times 10 to the power 6, 1 minus nu squared would yield 0.91, and the remaining terms, if you do the proper substitution properly, you would end up in getting a matrix, the D matrix, this formation. Yeah. To be consistent with the previous, I will use 5.4.6 here, 5.4.7, 5.4.8. Yeah. So what else do we need here to calculate the element stiffness matrix? We have the B matrix, we have the D matrix, then we have to find the transpose matrix of B. So for calculating, let's say, B transpose times D, we need this term for our calculation. You can simply transform the B matrix. Since this is the initial, the first example, I will do the transformation and write. So 30 times 10 to the power 6, let's factor this out, or take this out, common terms, and transform the matrix. So 1/6 matrix. This matrix is, let's say, sorry, 3 by 1 2 3 1 2 3 3 by matrix now becomes 6/3 once you do the transformation, transforming. So let's write it as, if you do the transformation now properly, you would end getting up. So you're simply transforming, taking the transpose of the B matrix. Just check whether I make a mistake. 10 minus 10. If there's a mistake, please let me know. 0, 20 minus 10, which is now a 6/3 matrix, and which should be multiplied by the matrix. So I will not write down the D matrix again here. So you have to multiply it by the D matrix, which is this matrix, of course, which we just derived, which we just obtained rather. So let's call this 8, 548, 549, So with a bit of simplification of 5.9, if you do your math right, you would be able to get equation or a result. So this is from here onwards, it's matrix manipulation. You have to be extremely careful when you're doing the hand calculation. Of course, if there are inverses to calculate, you can use the calculator to do so. So just check whether you get this answer. I have done it and separately, and I'm also checking whether I have got the correct answer now. 3.5. So in such cases, it's really convenient to take out the common factors wherever possible so that your hand calculation becomes simplified. Yeah. So now we have obtained the B matrix, D matrix, and of course the multiplication of the B transpose D matrix. What you have to do is use this equation for the element here, 5.4.3.3 equation. So we have already calculated this factor. We have to multiply it by B, and of course the constant values, the thickness and the area of the element, to obtain the element stiffness matrix for the first element. So once you do, let's say, substitute the values correctly in the equation, yeah. So okay, I will write down again here just for simplicity. So you need to substitute these values. Which I will not do. I mean, this again matrix manipulation. If you do the substitution correctly, the element stiffness matrix, of course, for the first element, you would get something like this in this formation. If you take out the common factors, I will take out the common factors out. And of course, there are 3 degrees of freedom as usual. We are dealing with the first node, X and Y displacements, and the next node is j node is given by the number 3, that is U3 and V3, and wait a minute, U1 V1, U3 V3, and the second node U2 V2. These are the corresponding, let's say, nodes that we are focusing, or we have to tackle, we have to use when we're using we are considering element number 1. So if you do the substitution correctly, you can even try it now, you would end up in getting the matrix information. If you are not able to do it now, you can, after the lecture, maybe you can work it out on yourself and see whether you get the correct answer. So this is a 6 by 6 matrix. The second row, this is 400, yeah. Third row, 60, 100, 0, minus 100, 60, minus 70, I guess now I was able to maybe motivate you to why we are required to use computers to do these calculations, because you may see now we have only used very small number of the simplest of all, only two elements, and we see how our matrices now it's really uh, complicated, or it becomes cumbersome to calculate these matrices. It's already a 6 by 6 matrix, and if we still use higher order elements and still use more number of degrees of freedom, let's say we use in the later sections, you will realize if we use a linear constant linear strain triangular element where the elements, or where the strain the stress uh, within the element is not constant, like in the constant stress triangular element, uh, the stresses vary linearly within the strain, rather the constant in the constant strain triangular element, the strains are constant, of course, but in certain problems, if we are required to further complicate it, I mean, we need to include add further degrees of freedom, use higher order functions to describe the displacements within the element. So you will see the nodes, number of nodes, or the number of degrees of freedom, as well as the complexity of the shape functions increases. Then it becomes, I mean, it becomes really hard, cumbersome to calculate, or to perform a simple hand calculation. So this is exactly the reason why we require numerical simulations, or we require the help of the computers to, and also efficient algorithms to solve such problems. Yeah. So um, we have already obtained the element stiffness matrix for element 1, and on top of each this matrix you can find the corresponding nodal degrees of freedom. So similarly, now I will quickly, since we have already walked through it quite slowly for the first element, we have to do the same procedure now for element 2. So if it would be nice, now you can take a piece of paper again. I mean, if you can really do it with me, so that you will save time, you won't have to do it again on your own. This would be really clear to you. So element number 2, of course, the other part of the triangle, or the square, rather the rectangle, the second element, we considered, okay, I, J, and M in the anticlockwise direction. We take I to 1. Of course, based on the original figure, J corresponds to node number 4 and M corresponds to node number 3. And if we take the let's say, if we assign the Cartesian coordinates, xi refers to 0, 0, xj refers to 20 and 0, m or xm refers to 20 and 10. Yeah. So likewise, like in the previous section, let's call this yeah, again, let's, for simplicity, let's also give this again a number, so that we will be you will not get confused with the supporting material which I will be uploading. So yeah, the next task is to find the B matrix. For finding the B matrix, we are required to find the elements of the B matrix, which is the beta and gamma terms, which is related now to the Cartesian coordinate systems or the nodal coordinates. So I, J, and M. What was the definition when we, so the x directions we were I, J, and M, Y clockwise, X anti-clockwise. So let's say if we want to calculate, let's say, the terms connecting to Y or beta terms clockwise and the gamma terms anti-clockwise. Let's see whether we are able to write down it now. So if you do it with me, it will be clear to you all. Now, beta I is, so we are talking of beta terms. We have to go in the clockwise direction. Beta, so if when we consider beta, we are talking about Y terms. Yj minus Ym. That is 0 minus 10 is equal to minus 10. Beta j is equal to Ym minus Yi. 10 minus 0, 10. Beta m is Yi minus Yj. 0 minus 0. Gamma terms. Gamma I related to now x terms. Anti-clockwise direction. I, so it should be expressed in terms of m and j. Xm minus xj. 20 minus 20, 0. Gamma j, xi minus xm and gamma m xj minus xi. I think you have got a hang of it, this method now. 20 minus 0 is nothing but 20. So this, I made a mistake. Minus 20. So let's call this equation 13. 5, 4, 3, 13. So using these definitions, or let's say beta and gamma values, we can write down the B matrix for the element number 2. 1 over 2a means again 200. That is the area. So we have 3 segments. Three segments of the B matrix. Sorry. So if we substitute the beta and gamma values here, using the previous equation, of course, let me write down it here so that it will be clear to you all. No, I have not written down it here either. Yeah, I have written down it here. 5.4.4. substitute in equation 5.5.4 would yield 10, 0, 0 minus 20, minus 20, 10, 0, 0, 0, 20, 20, and 0, 1 over inch. So similarly, we can find the D matrix. I will write down the D matrix without taking more time. So E times 1 minus nu squared and the corresponding terms 0, pounds per square inch. For this, I use this equation 547. Can use equation 547 again, just like you did for element number 1 to obtain the D matrix. Once you obtain the D matrix, then you can calculate take the transpose of the B matrix and multiply it by D like we did in the previous equation. You can do it on your own and try to verify with the, let's say, supporting material which I have uploaded. So you can refer to equation 5.4.16 maybe in the supporting material which I will be uploading. So this multiplication would yield let's say simplified equation, let's say, or would be equal to, if you do the, I will not substitute, you can see the substitution in the supporting material. So you would be able to get, let's take these factors out, 10 to the power 6, a matrix, a 6 by 3 matrix, 6 by 3 because we are only considering one element now, 0, 0, minus 3.5, 3, minus, minus. So we have neatly obtained the B matrix, D matrix, and the corresponding transformations. And so if you do the proper multiplication, the equations, let's say 5, 4, 18 in the supporting material, because I'm doing this to save some time, because otherwise we'll be writing large matrices. So it's important, since we have already gone through the important steps, I will not writing down supporting material. And this can be simplified to equation, let's say 5.4.9 given by 5.4.19, which will give quite large, let's say 6 by 6 element stiffness matrix for element number 2. 6 by 6 matrix for element number 2. So, and okay, for, let's say, for, because this becomes important for the next step, so I will have to write down the element stiffness matrix. I will write down 5.4.19 here, the element stiffness matrix for the element number 2 by taking these factors out of the matrix. maybe I only write without filling all the notations. 5.4.19 is what I have written here. So the element number 2 corresponds to node number 1, node number 2, node number 4, and node number 3. So node number 1, node number 4, and node number 3. Right. So now, if we are supposed to construct the global stiffness matrix. For this, we have to use the 2 element stiffness matrices we have developed. But we already know that the element if we consider an element, it has only 3 nodes, so there are only 3 degrees of freedom. So for each element, we obtain a 3 degrees of freedom, sorry, 6 degrees of 3 nodes. Each node has 2 degrees of freedom, meaning 6 degrees of freedom. So for element stiffness matrices, we obtain a 6 by 6 matrix. But we know if we consider the total structure, we have 4 nodes. Each node has 2 degrees of freedom. So there are totally 8 degrees of freedom. So the total global stiffness matrix should be 8 by 8. So in order to use the superpositioning method, we have to now construct each element into 8 by 8 matrices. Yeah. What we are trying to do is we are trying to now construct or expand the 6 by 6 element stiffness matrices which we developed for to the 2 elements into 8 by 8 matrix, so that we can simply use a superpositioning method to develop the total stiffness matrix for the total structure of, in this case, for the total model. Yeah. For element 1, again now, so since we have already developed the stiffness matrix, the only thing what we have to do is we hand it now for element 1 to the rank of the total global, the total stiffness matrix, that is 8 by 8. So we are expanding it from 6 by 6 to 8 by 8 by including the additional, let's say, degrees of freedom or the corresponding terms. So in the element number 1, we only had node number 1, 2, and 3. Yeah, node number 1, 2, and 3. So we only had number 2, the terms corresponding to node number 2, and the term corresponding to node number 3, and the rest we need to add v4 and in order to find the matrix. And these terms, the corresponding terms can be obtained, or you can simply refer to let's say equation 5.4, let's say 12 here, to save time. And you can use this subdomain or submatrix which we obtained from the previous session there, or not directly, because we will be taking some factors out. Okay, if we simply write down this equation without taking any factors out, you can directly write 5.4.12, use the elements which we obtained there, and the remaining degrees of freedom, because we don't deal with the node number 4, are obviously 0. All these terms are 0. There are 8 rows, so all these terms are 0. Similarly, for element number 2, we can write down again the stiffness matrix for element number 2 and expand it to 8 by 8. Yeah. So originally the element number 2 deals with only node number 1, 3, and 4. So we have to include node number 2. So U1, V1, this is what we have included in the previous. Included node number 4. This element stiffness matrix, we will be considering the effects of, let's say, the terms corresponding to node number 2, node number 3, node number 4. So apart from these elements, which are obviously 0 because it has no contribution, the remaining terms can be extracted based on equation what? 5, 4, 19. 5, 4, 19. Yeah, you can do it on your own and see whether you get the correct results based on the supporting material that will be uploaded. So if you do, let's say, now you have obtained, let's say, element stiffness matrices in the rank of the total stiffness matrix, that is 8 by 8. Now you can simply add the corresponding terms of the two matrices to develop the capital K matrix, that is the global stiffness matrix. I don't need to use an underscore, of course. Yeah, 8 by 8 matrix by simply adding the corresponding terms. Yeah, so which will include the 4 nodes U1 V1, U2 V2, U3 V3, and U4. And you need to add the corresponding terms so the corresponding terms at corresponding to of course position 1 1 1 1 of element number 1 and 1 1 of element number 2 has to be added, and you would obtain the corresponding term for the position 1 1 1 of this matrix. Similarly, you can fill all the other elements. So simply the superposition method is, you can apply the superposition method to obtain the total stiffness matrix. Of course, if required, you can use the direct stiffness method directly, of course, to construct this total stiffness matrix without using the superpositioning method. So there you can again add the corresponding terms to obtain the total stiffness matrix. So once you do it correctly, let's say all these details will be found in the supporting material, because in order to save time, you would end up in getting, let's say, since you already have the K matrix, the global stiffness matrix, this is capital K now, it's not the K, capital K refers to the global structure. Now we can directly relate it to the reaction forces of node number 1, node number 2, and node number 3. Yeah, node number 3, X is 5000, Y don't have a load, 4X refers to 5000. We have 5000 applied in the horizontal direction, no forces in the Y direction. The D matrix again, D1X, D1Y, D2X, D2Y, D3X, D3Y. First node is fixed, second node is fixed. This you don't know, and you would like to find out by solving the total stiffness matrix. Yeah. So now we can simply select the domain, or simply by eliminating the corresponding rows and columns which corresponds to 0, one can obtain the reaction force, let's say the displacements corresponding to node number 3 and 4, by also considering the corresponding part in the capital K matrix. So if I may write down the section corresponding to this capital K matrix, if you simply eliminate the rows and the columns, you should end up in getting, so on the left hand side I'm writing down the forces now. Fourth node in the y direction, and in the capital K matrix there are certain factors you would like to take out to be convenient, and since we have already taken 4 terms, it would be, we would end up in getting a 4x4 term matrix, 4x4 term matrix, 48, 0 minus 28, 14, minus 28, 12, 48, minus 26, 14, minus 80, minus 26, 87, d3x, d3y, d4x, d4y, and these terms since you are required to find let's say the values for the displacements in the x and y directions, you need to take the inverse, or you have to multiply the left and right hand side with the K inverse matrix of the corresponding terms, of course, in order to find this D matrix here. So because it's already like this, so in order to find this D matrix, you have to find of course the force matrix. You have to multiply it again by the D matrix here, K inverse, then you would be able to obtain the D matrix. Of course, even though I wrote the capital K matrix, it's not the capital K matrix per se. Let's say K subs, you have to take the sub matrix, which is not the total matrix, of course, the small portion of the total matrix, total force matrix, as well as the global stiffness matrix to calculate the displacements. And if you have done it correctly, you would end up in getting results or the final displacements as for d3x, you would end up in getting so d3x, d3y, d4x, and d4y. So just check whether you get the correct results. So these are the displacement which you would get if you do if you carefully solve the matrices, the displacements of the node 3 and node 4. You can see, since the traction forces are acting on the x direction, there's a significant displacement in the x direction, both in the fourth, third, and the fourth nodes. and there are very small amount of, let's say, in comparison to direction, of course, x direction, there's a small amount of displacement in the y direction, and of course we know this is due to the Poisson's effect. And since we landed on different numbers, we don't know really whether these are correct or not. Yeah, so in the supporting material you would find this under 4.5.4.27. yeah, so I may have skipped certain numbers, but I'm using the numbers so that I'm consistent with the supporting material. This is the reason. Okay, so since you have done the math and you have landed up in certain numbers, you don't have any value to compare. You don't know whether your results are right or not. Then we also discussed during the lab sessions, it is really important to do a very rough calculation, and as engineers you are expected to, you can use approximate theories or ideal conditions to see whether you are in the correct order of magnitude or whether you are completely wrong. So for that we can use let's say the knowledge which we obtain from the beam theory is able to express the displacements in beams using analytical equations. Let's say uh, typical, let's say a finite element simulation should converge to these results which we obtain from the analytical solution. Okay, for the axial displacements, subjected to traction forces, of course, for particular beams. We can use the knowledge obtained from the beam theory that the displacement corresponds to the load applied, as well as the geometry, as well as the Young's modulus of the material. So the total force, of course, applied is much, 10,000 pounds. The length is 20 inches. Area is let's say the corresponding area where the force is applied is 10 by 1, of course 10 inches by 1 inches, and the modulus of elasticity is 30 times 10, which will give us a displacement of around 670 plus 10 to the power minus 6 inches. So 670 plus 10 to the power minus 6 inches is what you get if you use the analytical solution from, let's say, the beam theory that you have developed. So you can see that the axial displacements are quite close to the values which we obtained at number 3 and for node number 3 axial displacement, and node number 4 axial displacements, with slight deviations. And of course these deviations are expected because we use very simplified solutions, only 2 elements, and which is a very coarse model. So if we would have used a more sophisticated model, meaning more fine measures, more number of degrees of freedom, or meaning more number of elements with higher order shape functions, of course, then we would be able to get approximate result, or get even much closer to this analytical solution, which we are quite familiar with when we talk about one-dimensional bar subjected to tensile forces. So as a conclusion, we can say that the result seems to be reasonably correct. So our finite simulation model seems to be all right, and the deviations can be attributed to the coarseness of the mesh, and the displacement, of course, in the y directions are due to the Poisson's ratio, the effect of the Poisson's ratio.